Hi, welcome back. Alright, so let's start with the homework for today's lecture. Did you think about it? Did you get an answer? Well, if I didn't, don't worry about it. Let's go over it together. So to resolve this problem, we have to delete the absolute value operation here, right? So we have to consider if x is bigger than 0. Okay, so we can say x, sin x divided by x. And we understand that if x is very small, we have sin x, almost, similar to x. So that's why, we can say it almost equals to 1. Correct? Okay. So if x is smaller than 0, okay, it's negative. Now we can say that sin x divided by x minus x, because when you get rid of the absolute value operation, you will have to put a minus here. Okay, in the condition where x is negative. So this time, since sin x and x are almost equal, so we can say it almost equals to minus 1. Okay? Alright, so if you got the correct answer, congratulations. Let's get back to our today's new content. Alright, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists, a positive number n. So when you choose x in this range, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0, and the range is about 0 to delta x. So there's always means the f(x) absolute value is smaller than m, which means the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have this function f(x). Okay, so it means if we have a limit here, like this one is called a. Okay, it's called a around at the point x0. So it means if we choose the neighborhood of x0, right, defined by the formula here, okay, this is like x0 minus delta, this is like x0 plus delta. So in this region, now we have the f(x) in this region. So for example, we can say the f(x) equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say f(x) absolute value of it is smaller than 8. So it means, it is correct, because on this point it is 5, on this point is 7, and now on this point is even lower than 5. So we can say that the function's value is also within a certain range. So we can say it is locally bounded. Yeah, locally bounded. Okay, so how can we prove this? Alright, so now we have the theorem listed here. Okay, so to resolve this problem, or to prove this theorem, the first step is I want you to write down the definition about this type of function limit. We have been using and practicing the definitions of limits so many times, and we have already seen that it is very useful for you to resolve the actual problems. And we're going to see the magic here again. So now, the definition is for any arbitrary epsilon, which is positive, and delta, which is also positive. So when you choose a certain x within a range defined by this formula, right? And then you can see that the distance between the function value and the limit a should be smaller than epsilon. Well, now you can see that the theorem and the definition are, so similar. Maybe we have, one thing here which looks a little different, right? So how can we change it? Maybe we want to change this, look similar to this. Okay, there we go. Let's start. So for the fx, now we can change it to fx minus a and then plus a. So we didn't change anything actually. Alright. I want you to remember this if it is first time for you to see such operation. So that's what I talked about at the first of this series of lectures. So I want you to culture your own mathematics thinking pattern. You're gonna see that last time we have something contradiction method, and we're gonna use that more later. And today we learn another method. We're gonna see here is called the identical deformation. Okay, I'm gonna use another color to circle this. Okay, so remember, this is our second one. Identical deformation. So in many proofs or calculation, to resolve the actual problems, we'll have to apply this to our steps. Okay, so this time let's continue. So for this guy, here, hopefully you remember something we learned so far in the middle of the high school in algebra 1, 2, 3 maybe. So for the absolute values, for expression like a plus b, well, as a whole, the absolute value of them is smaller or equal than a plus b's absolute values, right? Well, so this time we can do the similar thing here. Well, for this one, if you don't remember it, you can go back to check your textbook, or you can just simply try as many times as you want. Like a equals to 3, b equals to 2, you can try it. Or like a equals to 5, b equals to minus 1, you can try it. See if it is always right. Alright, so we suppose this is always right, okay? So now let's see. We take this part as a for example, so we can say fx minus a's absolute value, okay, plus the absolute value of a, correct? Okay, so we can say that. Okay, so I'll put a sign here, okay, which means the a and b's summation is smaller than a and b's separated absolute values, okay? So this time, we have noticed that this is what we have in the definition of the function limit. And this one is smaller than epsilon. So if this one is smaller than epsilon, which means this one plus a positive number because it's an absolute value, so it's a positive or equals to 0, can always say, okay, it must be smaller than epsilon plus absolute value of a, correct? So this time let's look at this all together. So I will put this in this more clear way. So it means fx's absolute value should be smaller than the epsilon plus the absolute value of a. Now we understand that epsilon is a positive number and a is also another positive number. So if we take the whole thing, Now we can say their summation is also positive. And we can give it a new name as m, okay? Because from the definition of m here, m is also positive. So we can say, wow, the summation of epsilon and the absolute value of a is also positive. So we can just name it as m. So this time, we have proved our problem. It just fx's absolute value should be smaller than m, and m is positive. Okay, so for today's homework, I would like you to review the definitions about the function limits and the series limits. If you're interested, or you forgot some part of it, yeah, it's really recommended. And the second part is I want to review the uniqueness property of limit, because since we have learned the two properties of limits, I want you to compare the similarity and the differences between those two properties. Okay, that's all for today. See you next time.